Welcome back, design junkies. You have power over your calculations, not over reality. Control what you can, respect what you can't.
Man, that's really the ultimate unforgiving truth of this entire industry, isn't it?
Oh, absolutely.
I mean, you can have the most beautiful, perfectly optimized mathematical model just, rotating on your CAD software. Every stress concentration factor is color-coded. Your finite element analysis is just
And it
pristine.
looks flawless on a screen.
Exactly.
Yeah.
But the absolute second a torch touches that steel plate on the shop floor, you are dealing with the physical universe. And the physical universe is incredibly messy.
It's a complete battlefield, honestly. Like, just imagine this scenario for a second. You spend months engineering a massive, maybe a 150-foot tall distillation column.
Huge investment of time.
Right, and the math is flawless. It's built, it looks beautiful in the shop, they load it onto this custom rail car, and it begins this massive cross-country journey.
Well, we know how those go.
Oh, yeah, because when it finally arrives at the refinery site, they put the lasers on it, and the entire column is just permanently warped. It never even saw a single drop of chemical product or, a single sigh of operating pressure, and it is entirely compromised.
Which is a total nightmare for everyone involved.
Exactly. So today, our mission for this deep dive is to explore that exact gap. We are looking at the massive chasm between those pristine engineering models of pressure equipment and the brutal, often chaotic reality of manufacturing, shipping, and actual real-world operation.
Because we're basically dissecting what actually happens when perfect math meets imperfect steel.
Spot on. And that reality check matters to you, the listener, whether you are the design engineer plugging numbers into a simulation or the fabricator on the shop floor trying to make two mismatched plates fit together.
Or even the quality code inspector signing up on that final hydro test. Every single one of you is battling the exact same physics
We
here.
really are. So in this deep dive, we are going to just tear into the biggest pain points across the entire life cycle of pressure equipment.
Yeah, we'll be debunking some very dangerous, widely held myths and highlighting exactly how you can avoid these catastrophic mistakes in your own projects.
So let's start right at the genesis of a vessel, which is the blueprint. There is this really pervasive illusion that a perfect blueprint basically guarantees a perfect vessel.
Right, which is just not true.
And not at all. But diving into the source material, there's a really fundamental difference in how these vessels are even conceptualized from the start. The texts heavily emphasize the difference between designing by rule versus designing by analysis.
It is a crucial distinction, honestly, and it sets the stage for everything that follows. When you look at the industry workhorse standard, which is the ASME Boiler and Pressure Vessel Code, specifically Section 8, Division 1, it is fundamentally a design-by-rule standard.
Okay, so what does that actually mean in practice?
What that means is you don't actually have to do a detailed, granular, microscopic evaluation of every single localized stress point in the entire vessel. You don't need a supercomputer to do it.
Oh, that's convenient.
Very. Instead, the code gives you established, proven formulas for the thickness and the stress of basic components. You literally just plug in your pressure, your temperature, your material, and your diameter, and the rule just tells you how thick the steel needs to be.
Which sounds vastly easier and, well, much faster. But I have to imagine there's a catch there, right? Like, if we aren't mapping every single stress point, how do we know a nozzle attachment isn't going to just randomly rip open?
The catch is brute force. That is the fundamental trade-off. Because you aren't calculating every single localized stress like, say, the sharp bending stress where a flat head meets a cylindrical shell, the code forces you to use a significantly higher safety factor.
Okay, so they just overbuild it.
Exactly. The code committee acknowledges that those high, localized, uncalculated stresses absolutely exist.
Yeah.
But the philosophy is essentially, since we don't precisely know the magnitude of those complex local stresses, we will just make the entire vessel thicker and heavier.
Just to absorb whatever those stresses might be.
Right. It's a massive penalty on the design weight,
Yeah.
and therefore the material cost, but it requires a fraction of the exhaustive mathematical analysis.
Okay, so if we are using this design-by-rule approach to save on engineering hours, we rely really heavily on a concept called membrane stress analysis. The sources lean on this heavily.
They do, yeah.
It basically assumes that the vessel behaves like a thin shell specifically, where the radius divided by the thickness is greater than 10. But when you look at the assumptions this analysis makes, they seem almost, I don't know, comically idealized.
Oh, they are highly idealized. They're simplifying assumptions that are mathematically necessary just to make the rule-based formulas work on a standard piece of paper.
So what are it assuming exactly?
Well, membrane stress analysis assumes that the stresses resulting from internal pressure are completely perfectly uniform across the entire thickness of the vessel wall. It assumes they act purely tangentially to the surface. And critically, the most dangerous assumption is that it treats the wall as having zero resistance to bending. It literally treats a massive steel vessel exactly like a rubber balloon membrane.
Right, but a balloon expands perfectly. Steel isn't rubber. If I blow up a balloon, the rubber stretches uniformly in all directions. When I pressurize a half-inch thick steel cylinder, it really wants to hold its shape.
Exactly. Let's look at the true physics for a second here. In a true biaxial stress state, for a thin-walled cylinder, you have your longitudinal stress, which is the pressure trying to blow the end caps off.
So pulling the cylinder along its length.
Right. And then you have your circumferential stress, which is also known as hoop stress. That is the pressure trying to split the cylinder open right down the middle. And here's the kicker. Hoop stress is actually exactly twice as large as longitudinal stress.
Which is why when you boil a hot dog, it always splits lengthwise down the side, not across the middle. The hoop stress rips it apart.
That is a perfect analogy, actually. The hoop stress dictates the required thickness of the cylinder. Now, the radial stress, the pressure pushing directly, microscopically outward into the thickness of the wall itself,
Right.
is so incredibly small compared to the hoop and longitudinal stresses that the membrane theory just ignores it entirely,
It just pretends it's not there.
pretty much. But here is where the whole balloon illusion shatters. No real-world pressure vessel is a perfect, uninterrupted, infinite cylinder.
Right, because you have to actually use the thing.
Exactly. You have heavy forged heads closing off the ends. You have heavy steel support lugs welded to the side. You have variations in plate thickness. You have giant holes cut into the shell for nozzles and manways.
And obviously, none of those things stretch like a rubber balloon.
Not even close. All of those rigid deviations from a perfect cylinder create massive bending stresses on top of the uniform membrane stresses. The structural load always wants to find the stiffest path to ground.
Oh, I see.
So the load gets diverted from the flexible, thin parts of the vessel and concentrates heavily at the rigid parts, like the crotch corner of a nozzle.
And this directly leads to one of the most misunderstood concepts in the text, which is how we handle those localized stress spikes.
Yes, the secondary stresses.
Right. The misconception revolves around these secondary stresses. A secondary stress is basically a stress developed by the constraint of adjacent parts, like that rigid nozzle fighting against the flexible shell.
Exactly.
And the golden rule you hear repeated constantly in the industry is that secondary stresses are self-limiting. But what does that actually mean in plain English?
The theory of a self-limiting stress is actually quite elegant on paper. It means that once the structure yields, once it permanently plastically deforms just a tiny microscopic amount at that highly stressed local point, the stress is instantly relieved.
So it just shifts the burden.
Basically, yes. It's redistributed to the surrounding metal. The structure basically flexes to physically accommodate the load, and the concentrated stress drops. Because it's highly localized, that microscopic yielding won't lead to a catastrophic failure of the entire vessel in a single application of that load.
Wait, I see a massive flaw in this. That whole elegant theory completely relies on the material being able to bend and yield without snapping. It assumes the steel is ductile.
You've hit the exact nail on the head. That is the massive, dangerous misconception. Engineers and designers often apply the concept of self-limiting secondary stresses universally, like it's some law of nature.
That it's not.
No. If your material is brittle, the entire definition of a self-limiting stress violently falls apart. A brittle material mathematically and physically cannot yield to reduce the load.
It can't flex at all.
It cannot flex. It just rigidly takes the stress, absorbing the energy until it reaches its ultimate tensile limit, and then it fractures. Suddenly, catastrophically, and usually without any warning whatsoever.
I picture it like a tree in a severe windstorm. Like if you have a living willow tree, the wood is incredibly ductile. The wind hits it. The massive secondary stresses build up where the branch meets the trunk, but the branch bends.
It yields.
Exactly. It permanently yields a bit, changes its aerodynamic shape, and the stress of the wind is redistributed. That's your self-limiting secondary stress.
But what if you have a dead, dry twig?
It's a completely different story.
Right. You apply that exact same wind force, and it doesn't bend an inch to relieve the stress. It just snaps in half instantly.
Yeah.
So the ASME math assumes you are building a willow tree. But what happens when the environment turns your vessel into a twig?
That is the ultimate nightmare scenario. And it's exactly why current pressure vessel codes strictly require the use of verified ductile materials. But the physical universe is tricky.
How so?
Well, you might buy perfectly ductile carbon steel, but certain environmental conditions, specifically low temperatures, can cause a ductile carbon steel to undergo a phase transition. It starts to behave exactly like glass.
This is known as the ductile to brittle transition temperature. We have documented cases where brittle fractures have completely destroyed low-carbon steel vessels during a routine hydro test simply because the test water was pulled from a cold winter main at around 40 or 50 degrees Fahrenheit.
Just from cold tap water.
Just from cold water. And there was a minor microscopic flaw in a weld, and the whole thing shattered.
That is terrifying. Actually, this perfectly lines up with a huge question people constantly ask about this topic. It's about impact testing.
Oh, yeah. A huge pain point.
Right, because if cold temperatures turn steel into a twig, the codes mandate strict Charpy V-notch impact testing to prove the steel can actually take a hit at the minimum design metal temperature, or MDMT.
Yes, they do.
But the texts point out that impact testing every single heat of steel is massively expensive and completely wrecks procurement schedules. So how do engineers avoid the massive expense of impact testing for low temperatures?
It is a massive bottleneck for projects. But the code does provide 3 primary, perfectly legal engineering workarounds to avoid the expense of impact testing. Option 1 is probably the simplest. Upgrade your metallurgy.
So just buy better steel.
Exactly. Spend a little more money up front on a steel alloy with inherently better low-temperature toughness, like moving from a standard carbon steel to a fine-grained normalized carbon steel, or even jumping up to a stainless steel.
Okay, that makes sense. You pay more for the metal, but you completely bypass the testing requirement and the schedule delay.
Right. Now, option 2 is entirely counterintuitive, which is why it confuses so many people. You increase the thickness of the component.
Wait, you actually make it thicker and heavier than the internal pressure requires?
Yes, exactly.
Hold on, you just lost me. How does making a plate thicker help with cold temperature brittleness? I mean, the Titanic was made of thick steel, and that cold water turned it brittle enough to fracture. Wouldn't a thicker twig still snap?
I know it sounds wrong, but it really comes down to the ratio of actual stress to allowable stress. Let's say your pressure requires a wall thickness of ½ inch, but you intentionally build it an inch thick.
Okay, double the thickness.
Right. The actual stress the metal experiences under pressure is suddenly cut in half. It is massively overdesigned for the load.
Oh, I see.
The code recognizes, through decades of empirical fracture mechanics data, that at very low stress levels, the risk of a crack propagating into a brittle fracture plummets dramatically. So by artificially lowering the stress ratio via extra thickness, the code allows you to operate at colder temperatures without proving the impact toughness.
Okay, that makes perfect sense now. You're basically starving the potential crack of the energy it needs to actually tear through the metal. That's brilliant. And what is option 3?
Option 3 is more of a process control change rather than a physical design change. You decrease the allowable pressure at that specific low temperature condition.
How does that work in practice?
You basically write an operating procedure that says, yes, the vessel metal gets down to -20 degrees Fahrenheit during a winter shutdown, but we have interlocking systems to ensure the internal pressure is strictly vented and drop to 20% of maximum during that thermal state.
Because if the pressure is low, the stress is low.
Exactly. The energy is low, and again, you bypass the test.
That is incredibly practical engineering right there. You're manipulating the stress, not just blindly testing the metal. But this whole idea of the environment attacking the vessel is actually the perfect setup for our next major pain point.
The environmental chaos.
Exactly. We design these vessels to hold explosive pressure inside, but the world outside is actively trying to tear them down. So let's talk about the wind. Because sitting in an office, you think of wind as just a steady, static pushing force against the side of a tank. But it's not, is it?
Not at all. Treating wind as a static load is a real beginner's mistake. Wind is highly dynamic. When fluid, and remember, air is technically a fluid, flows past a tall cylindrical column, it doesn't just split cleanly and rejoin perfectly at the back.
What does it do?
As the wind speed increases, the flow actually separates. It creates alternating, swirling vortices on the leeward side, so the back side of the vessel. This phenomenon is called vortex shedding. Think of the Kármán vortex street you sometimes see in satellite photos of clouds passing over an island.
Oh, I've seen that. It looks like a repeating, alternating zigzag pattern of swirls.
Exactly. And as each of those alternating vortices detaches from the steel surface, it creates a localized low-pressure zone. This literally pulls the massive steel vessel slightly to that side.
Wow.
And because the vortices alternate left, right, they induce an alternating cyclic force that physically pulls the vessel back and forth. And this is completely perpendicular to the actual direction the wind is blowing.
The numbers and the sources on this are absolutely terrifying, honestly. They calculate that a standard vertical column with a fundamental period of vibration of just 1 second, if subjected to this vortex shedding for just 3 hours a day over a 30-year operational lifespan,
It adds up fast.
it will experience 120 million fatigue cycles. 120 million times that steel is pulled back and forth.
And that, right there, is how structures die. Fatigue is a cycle-dependent, accumulative phenomenon. Every single one of those 120 million cycles is doing microscopic damage to the steel.
Where does the damage happen?
The damage accumulates at the granular level, and it almost always concentrates at regions of high structural stiffness, like the heavy weld where a nozzle attaches, or the base skirt where it bolts to the concrete.
So the stiffest parts take the beating.
Always. Eventually, after millions of microscopic fluxes, those tiny slip bands in the metal link up to form a microscopic crack. Once that crack exists, it acts as an extreme stress multiplier, and it just propagates faster and faster with every passing cycle until the vessel tears open.
So how does the design engineer stop this? I mean, you can't exactly turn off the wind.
You can't. What you have to do is accurately calculate the natural frequency of the vessel and ensure it doesn't synchronize with the frequency of the vortex shedding. If they synchronize, you hit resonance, and the vessel will literally shake itself to pieces.
Kind of exactly like the famous footage of the Tacoma Narrows Bridge collapsing.
Precisely like that.
But the text points out a huge pitfall here. Engineers calculate the frequency of the beautiful bare steel cylinder they designed in CAD, and they completely forget everything else.
Yes, forgetting the accessories is a classic, catastrophic mistake. You cannot just calculate the frequency of the bare shell. A real column has tons of mass attached to it out in the field.
Like what?
You have heavy steel ladders, wraparound maintenance platforms, massive vertical pipes full of fluid hanging off the side, heavy thermal insulation. All that extra mass drastically lowers the natural frequency of the column, changing how it sways.
And if you ignore the platforms in your math,
your resonance calculation is garbage. Furthermore, the text highlights a major window of vulnerability. When a tall column is first craned into place and erected on site, it is incredibly susceptible to wind vibration because it's completely empty and lightweight.
right, it doesn't have the heavy internal process fluids anchoring it down yet.
Exactly. That is why the text strongly advises grouting the vessel base ring immediately after erection. Do not wait for the piping crew to show up. Get the concrete grout poured and cured under the base plate to lock it to the foundation.
That makes total sense.
You will also frequently see external attachments on tall stacks, those spiral fins or strakes wrapped around the top third of the column.
Yeah, I always wondered what those were.
Those aren't for decoration. They're aerodynamically designed specifically to break up the wind flow and physically prevent those alternating vortices from forming in the first place.
That is so cool. Okay, so wind is a slow, agonizing, vibrating death over 30 years. But let's talk about an environmental killer that is instantaneous and absolutely violent, which is external pressure and vacuum collapse.
Oh, this is a big one.
Because intuitively, when we think of a pressure vessel failing, we picture it exploding outward like a bomb. But imploding inward seems almost more dangerous because it completely changes the rules of the physics.
It's an entirely different physics, and it catches a lot of people off guard. When a vessel is subjected to internal pressure, the steel wall is in tension, it's being pulled apart, and steel is incredibly strong in tension.
Right.
But under external pressure, or if an internal vacuum forms inside the tank, the steel is pushed inward, it is in compression. And when you have a thin shell structure in compression, the governing failure mode is no longer the yield strength of the metal.
What is it then?
It is elastic instability. It is buckling.
So geometry becomes the master, not material strength.
Precisely. A vessel could fail from a vacuum collapse at a stress level that is phenomenally lower than the actual yield point of the steel. It stops being a question of how strong is the steel and suddenly becomes a question of how stiff is the shape.
Wow.
And unlike a tension failure, which might start as a slow leak or a visible bulge, elastic instability failures happen suddenly, without warning, by the catastrophic, instantaneous crushing of the component. It literally happens in the blink of an eye.
Which begs the question, unless we're talking about a dedicated vacuum chamber testing space equipment, how do these vacuums even happen in a standard chemical plant?
Well, sometimes they are intentional. For example, a vacuum distillation column operates under a vacuum to lower the boiling point of the crude oil. But far more often, it's an entirely inadvertent operational error.
Like somebody pushes the wrong button.
Basically, one of the most common causes happens during routine maintenance. A vessel is steamed out to clean it of hydrocarbons, which is very common in refineries. So the vessel is full of hot steam, and then a technician closes the valves. As that trapped steam cools down against the ambient air outside, it condenses back into liquid water.
And water takes up a tiny, tiny fraction of the volume of steam.
Exactly. That massive, rapid volume reduction pulls a severe vacuum inside the sealed tank. If that vessel wasn't explicitly designed to handle a full vacuum, it will instantly crush inward like a stepped-on soda can.
That is brutal.
Another extremely common real-world error is draining a heavy liquid from a tank without properly opening a large enough vent at the top. The massive weight of the departing liquid pulls a vacuum behind it, almost like pulling the plunger back on a sealed syringe.
Actually, speaking of pulling vacuums and material weight, this is the perfect time to bring in another huge question from the field. It's about storing materials.
Okay, let's hear it.
If someone needs to design a massive storage bin or silo for solid materials like grain or coal or plastic pellets, my brain tells me that it's basically just a volume of heavy stuff pushing on the walls. Can an engineer just use standard liquid hydrostatic pressure math to design the silo walls?
No, absolutely, unequivocally not. That is a massive structural failure-inducing mistake that has collapsed countless silos over the decades.
Really? Why?
Because liquid pressure is beautifully predictable, it is isotropic, it pushes equally in all directions, and the pressure increases perfectly linearly with depth. Water doesn't care about friction. Solid materials, however, behave entirely differently because of internal friction and particle interlocking.
So the grain pellets physically lock together under pressure?
Yes, they tend to bridge and form structural arches across the diameter of the bin.
Wait, like a stone arch in a Gothic cathedral?
Exactly like that. It is the exact same physics. And just like an architectural arch transfers the weight of the stone ceiling out into the walls, that internal bridge of solid grain transfers the massive vertical weight of all the material above it directly outward.
Into the steel walls?
Right, into the walls of the steel bin as a concentrated horizontal force component. At the same time, because the arch is holding the weight, it drastically reduces the vertical pressure resting on the bottom floor of the bin.
Oh, wow. So if I use water math, I'm expecting all the weight to be at the bottom, but the grain is actually throwing all that weight horizontally into the middle of the walls.
Exactly. The force distribution is entirely nonlinear and totally unlike fluid dynamics. The walls of a steel silo are not designed to be flying buttresses. If you designed a tall silo using water pressure math, the walls will inevitably buckle from the horizontal thrust of those internal solid arches, or the silo will fail completely during emptying when those arches violently collapse.
That is terrifying.
You absolutely must use specific, complex, granular mechanics formulas like Jansen's equation to calculate those varying lateral loads.
That is mind-blowing. Okay, returning to vacuum and external pressure real quick. How do we reinforce vessels against crushing? I mean, we don't just make the entire wall 2 inches thick, right? We use stiffening rings. But are they just ribs? Just throwing extra metal on the outside to stop the crushing?
They act as structural ribs, yes. The math behind buckling shows that the longer a cylinder is, the less external pressure it takes to crush it. Stiffening rings artificially reduce what's called the unstiffened length of the cylinder.
Okay, breaking it up.
Right. By welding these heavy steel rings around the circumference, you break a long, vulnerable cylinder up into several shorter, vastly stronger segments. You massively increase the moment of inertia and therefore its resistance to buckling. But what's fascinating here is how vastly different this entire design process is compared to internal pressure.
How so? Isn't it just another formula you look up?
It's not at all. Designing for internal pressure is a very straightforward, deterministic calculation. You know the pressure, you know the diameter, you know the allowable stress of the metal. You plug it into the formula and it spits out the required thickness. Done.
Right.
But designing for external pressure is a highly iterative trial and error procedure. There is no single magic formula. You as the engineer have to assume a shell thickness, assume a stiffener size, and assume a spacing distance. Then you run the complex calculations using specific geometric material charts provided by the CADE, and you see if your assumed combination passes.
And if it fails?
If it fails, you have to go back to the drawing board. You maybe bump up the shell thickness by 1/8 of an inch, or maybe you add more stiffening rings closer together, or you choose a heavier ring profile. And then you run all the math again. It is a constant balancing act of cost and geometry.
The text specifically warns against placing these stiffening wings directly over circumferential weld seams. Why is that? It seems like welding a ring over a weld would just make that spot super strong.
It does the exact opposite, actually. Weld seams are inherently areas of localized residual stress, potential slight misalignments, and metallurgical discontinuities due to the massive heat of the welding arc.
Oh, right. The heat alters the metal.
Yes. The area right next to the weld, the heat-affected zone, is often the most brittle part of the metal. If you put a heavy, rigid stiffening ring directly over a circumferential weld seam, you are taking all the massive bending stresses from the vacuum load and concentrating them rigidly right at the most vulnerable, potentially brittle point in the entire shell.
That sounds like a recipe for a crack.
It is. You always want your stiffeners welded to the clean, continuous base plate. Interestingly, though, the text also notes a really neat practical trick here.
What's that?
If you plan your stiffener spacing correctly during the trial and error phase, those rings can double as the physical support brackets for the external thermal insulation of the vessel. It saves you from having to weld hundreds of additional little clips.
That is a brilliant practical tip. Optimize the math to serve the field. Okay, so the wind is trying to vibrate it to death, the grain is trying to push the walls out, and the vacuum is trying to crush it inward. But honestly, as I mentioned in the intro, a lot of vessels might not even survive the trip from the shop floor to the plant. Let's dig deep into the transit nightmare.
Oh man, this is a profound, incredibly expensive source of frustration in the industry. You spend thousands of engineering hours, you spend millions of dollars manufacturing a flawless, code-stamped pressure vessel, and it arrives at the job site permanently damaged.
Just a total disaster.
The project schedule is instantly destroyed, the budget is blown out of the water, and the legal finger-pointing begins immediately.
And reading the sources, it happens because vessels are almost entirely designed for their final operating state, not their horizontal transit state. A massive distillation column is designed to sit vertically on a reinforced skirt, taking compressive gravity loads straight down its longitudinal axis. But to get it to the site,
You have to lay it down horizontally on a multi-axle truck, a rail car, or a barge.
exactly, you are rotating a structure 90 degrees and subjecting it to gravity in a way it was never optimized for. And beyond just gravity, each of those transportation methods induces completely unique, one-time-only dynamic shock stresses.
Yes, the transit shocks are brutal.
If it goes by sea or barge, it has to endure the cyclic rocking, pitching, and heaving of the ocean waves for weeks. Those cyclic inertial forces on a heavy vessel can be tremendous.
Absolutely.
If it goes by rail, you have to account for the lateral centrifugal forces of the train whipping around corners at high speeds, plus the massive longitudinal shock forces up to several Gs of acceleration when rail cars slam together during coupling in the rail yard.
And these transit forces can induce massive bending moments that permanently plastically deform thin-walled trade columns before they ever see a single drop of process fluid.
The text mentions a really specific, highly counterintuitive danger here regarding shipping saddles. These are the temporary curved cradles the vessel rests in during transport. The golden rule seems to be stick to exactly 2 saddles. Why?
It seems wrong, right?
Yeah. My common sense tells me if I have a really long, heavy tube, I should put 3 or 4 saddles under it to spread the weight out. More support equals less stress, right? Why is adding a 3rd saddle a bad thing?
Your common sense is exactly what destroys vessels. It comes down to structural mechanics and beam theory. If you support a rigid beam or a vessel on exactly 2 saddles, the structure is what we call statically determinate.
Which means...
What that means is we can use basic, reliable physics equations to calculate exactly how much weight is bearing down on saddle A and saddle B. And this is true regardless of slight imperfections in the support structure or the road beneath it. Because we know the exact load at those 2 points, we can design the vessel shell at those specific locations, perhaps with internal stiffening rings, to handle that precise localized stress.
Okay, so 2 points make a line. We know the math. What happens the second I add a 3rd saddle in the middle to quote-unquote help out?
The absolute moment you add a 3rd saddle, the structure mathematically becomes statically indeterminate. You now have zero guarantees about how the massive weight of that vessel is actually apportioned among the three supports.
Because the ground isn't perfectly flat?
Because here's the brutal reality. The real world isn't perfectly flat. If the flatbed trailer flexes as it drives over a raised railroad crossing, or if the barge deck isn't perfectly true, or even if one saddle was built a quarter-inch taller than the others, the entire weight distribution shifts violently.
Oh, wow.
Suddenly, that middle saddle might be taking 90% of the entire weight of the
Well,
vessel.
I see. It acts like a fulcrum on a seesaw.
Exactly. The vessel shell was never designed for that massive concentrated point load right in the middle. The entire weight of the column bears down on that slightly higher third saddle, and it can literally buckle the shell or punch a hole right through the steel wall.
It's exactly like moving a giant, multi-tiered, delicate wedding cake. You spend hours in the kitchen perfectly balancing the tiers, and then you put it in the back of a delivery van and hit a pothole. All that perfect design work doesn't matter if the delivery mechanism introduces a shock it wasn't built to absorb.
That's exactly it.
So who actually takes responsibility for this? Do the ASME code guys sign off on the shipping plan? Is the inspector checking the saddles?
Usually, no. And that right there is the fundamental pain point. The pressure vessel codes explicitly cover pressure containment and operating loads. The vessel design engineer's priorities are internal pressure, temperature, and operating conditions.
Which makes sense for them.
Right. But the logistics and transportation guys' priorities are completely different. Axle weights, bridge height clearances, and tie-down strap ratings. Often, these two isolated worlds do not communicate effectively.
That sounds like a massive blind spot.
It is. The design engineer assumes the logistics company knows how to move it safely, and the logistics company assumes the massive steel tank is just indestructible. The text strongly emphasizes that someone, usually the purchaser or an integrated project engineer, must explicitly take responsibility for analyzing the shipping loads, because they rarely coincide with the operating design concerns.
Okay, let's trace this back even further. Before it even gets onto that flatbed or barge, it actually has to be built. And this is where the pristine math of the CAD engineer violently meets the sparks, the heat, and the sweat of the welder. Let's talk about the shop floor reality, starting with manufacturing misalignments.
Everything starts with the raw material, which is usually just flat steel plate. You have to physically force that flat plate into a perfect cylinder. If you are dealing with very thick plates, say over 20 or 30 millimeters, you are running them through massive mechanical plate rollers.
Right, huge industrial machines.
But thick steel has a tremendous metallurgical memory. It desperately wants to spring back to being flat after it leaves the rollers. Achieving perfect, flawless circularity on thick plate is almost physically impossible.
Okay, so thick plate fights back. What if you have a low-pressure tank using really thin plate? That should be easy to roll, right?
Thin plates, like under 10 millimeters, have the exact opposite problem. They completely lack rigidity. They might roll easily, sure, but when you apply the massive concentrated heat of a welding arc to join the longitudinal seam, the physics of thermal expansion take over.
The heat distorts it.
Oh, massively. The steel expands locally at the weld and then contracts violently as it cools. The thin plate warps, twists, and distorts just from the localized thermal input of the welding process. So right out of the gate, before you even assemble the vessel, your mathematically perfect CAD cylinder is actually slightly oval, slightly warped, and fighting massive internal residual thermal stresses.
And then you still have to put the end caps on, the heads.
Yes, the head-to-shell alignment is a notorious nightmare on the shop floor. The heads are usually formed by a completely different process, often spinning or pressing over a die, which is a severe cold deformation process.
Okay, stretching the metal.
Right. Because of how the metal physically stretches and thins out during forming, particularly at the knuckle radius, a spun head is often ordered from the mill slightly thicker than the shell plate to ensure it still meets the minimum code thickness after it stretches.
Makes sense on paper.
On paper.
Yeah.
But now, picture the welder. They are trying to fit an imperfectly round, warped, slightly thicker heavy head onto an imperfectly round, thinner shell.
How do they even do it? It sounds like trying to fit a square peg into a round hole while it's literally on fire.
They do it with brute force. Fitters will weld temporary steel dogs onto the plates and use heavy wedges and sledgehammers. They essentially hammer and physically force the two mismatched pieces into alignment just long enough so they can lay down the tack welds.
That sounds aggressive.
It is. But this forcing creates what inspectors call bulging or peaking. The thinner shell is physically permanently distorted to meet the contour of the head.
But Wait, didn't we just establish that changing the geometry ruins the membrane's stress math?
Exactly. This geometric misalignment between adjacent plates creates a massive, severe, localized increase in stress when the vessel is eventually pressurized. The membrane forces no longer flow smoothly in a straight line across the joint. They hit the offset, and they have to essentially jog around the misalignment.
Creating bending,
Yes, this offset creates a localized bending moment right at the weld seam.
which is already the weakest, most heat-affected link, and this brings us to what I call the prettiness trap. I found this detail absolutely fascinating in the sources. So a welder completes a joint, maybe the alignment wasn't perfect, so there's a bit of a step, or the weld crown is a bit lumpy.
Happens all the time.
Right. To make it look good for the strict inspector, or just out of personal pride in their craftsmanship, they take a heavy grinder and smooth the entire weld down so it looks perfectly, seamlessly flush with the plate.
And in doing so, they might be inadvertently destroying the vessel's structural integrity. Excessive grinding is incredibly dangerous and a massive headache for inspectors.
Why is making it smooth so bad?
Because the design engineer calculated a very specific minimum steel thickness required to hold the pressure. Then they added a corrosion allowance on top of that, say, an extra 3 millimeters of sacrificial steel, specifically to account for the metal that will rust or chemically etch away over the vessel's 20-year operational life.
Ah,
If the welder takes a grinder and shaves away 4 millimeters of solid steel to make a lumpy joint look pretty and blend to misalignment, they have illegally reduced the effective wall thickness below the minimum safe requirement. They have literally erased the corrosion allowance. The vessel is now fundamentally unsafe and doomed to fail prematurely before it even leaves the shop.
that is wild. Pride literally comes before the fall. And speaking of welding nightmares, the sources highlight the absolute torture of small nozzles. The text notes that getting a good weld profile on nozzles under 50 millimeters in diameter is incredibly difficult. Why is a smaller hole harder to weld than a big manway?
It's a severe ergonomic and physical challenge. With a large manway, the welder has room to move, adjust their angle, and control the heat puddle. With a tiny 50 millimeter nozzle, the angles are incredibly tight.
Too small to get in there.
Exactly. The heat from the arc builds up intensely and quickly in that small, localized area, and the welder simply cannot physically manipulate the electrode or the TIG torch optimally around that tight radius. This frequently leads to severe, critical weld defects.
What kind of defects?
You see a lot of undercut, where the intense arc actually gouges away the base metal next to the weld, creating a sharp stress trench that acts as a perfect crack initiator. Or you see incomplete penetration, where the weld metal doesn't fully reach the root of the joint deep inside, leaving a sharp void completely hidden inside the wall.
And how do we find those hidden voids? Because we clearly can't just trust that it looks perfectly flush and pretty on the surface.
This is exactly where non-destructive testing, or NDT, comes in. Visual inspection is really just the bare minimum first step. To look deep inside the solid steel weld, we primarily use radiography, literally X-raying or gamma-raying the weld. We place a radioactive isotope on one side of the weld and photographic film on the other.
Like getting an X-ray of a broken bone.
Exactly. Dense solid steel blocks the radiation, so the film is lighter. But if there's a void, like trapped gas porosity, a line of trapped slag, or an internal crack, the radiation passes right through that empty space, exposing the film and creating a dark spot. That finds our volume defects. But radiography isn't great at finding microscopic cracks right on the surface. For those defects that break the surface but might be totally invisible to the naked eye, we use surface methods. For carbon steels, we use magnetic particle inspection.
How does that work?
You induce a strong magnetic field across the weld. If there is a microscopic surface crack, the magnetic sex lines are forced to jump out of the steel and bridge the gap of the crack, creating a flux leakage field. You then spray the area with fine iron powder.
And it sticks to the crack.
Exactly. The iron powder is magnetically drawn perfectly to that flux leakage, highlighting the invisible crack as a bright, visible line. For non-magnetic materials like stainless steel, though, we use dye penetrant testing.
Dye penetrant.
Yeah, you clean the weld, spray a highly searching, brightly colored liquid dye that uses capillary action to pull itself deep into any microscopic surface cracks. You wipe the surface clean, and then spray a white developer powder. The developer acts like a sponge, using reverse capillary action to suck the trapped dye back out of the crack, creating a bright red bleed mark right against the white background.
That is fascinating. The physics of inspection is just as complex as the physics of the design. But even with all of that incredible NDT, the text is very clear on one thing, except that some physical misalignment on the shop floor is just inevitable. It's the physical reality of forming raw steel. But you have to strictly monitor the step or offset between plates, especially on longitudinal welds.
Yes, the codes have strict tolerances on exactly how much offset is legally allowed, and they are much stricter on longitudinal welds, for the reason we discussed earlier.
Right, the hoop stress.
Exactly.
Hmm.
A cylindrical vessel under internal pressure experiences twice as much hoop stress, the stress trying to split it open lengthwise, as it does longitudinal stress. Therefore, those longitudinal weld seams are taking double the punishment of the circumferential seams. They are far less tolerant to the massive, localized bending stresses caused by misalignment.
Okay, so the welders have wrestled the warped steel into shape, the grinders have been told to put their tools down and leave the corrosion allowance alone, and the NDT text says the X-rays and dye penetrant are completely clean. Now, the official code guys step in to definitively prove the vessel won't explode, the hydrostatic test. But reading the sources, I have a massive question. What does that test actually prove? Because there are some massive industry-wide misconceptions here.
This is perhaps the single most dangerous misconception in the entire engineering and operational field. The standard hydrostatic test usually pressurizes the vessel completely full of water to 130% or 150% of its maximum allowable design pressure.
Okay, a big overpressure.
Right. They hold the pressure, the inspector walks around with a flashlight looking for drips, and if it holds, they stamp it. People walk away thinking, great, we put it to 150%, it survived, therefore this vessel is completely unconditionally safe for its entire 30-year design lifespan. That is emphatically, dangerously false.
Hold on. You're telling me the ultimate industry standard test, the one the inspector signs their name on, doesn't actually guarantee the vessel won't fail next month? What is it actually testing then?
A pressure test only tests the vessel's resistance to static principal stress.
Hmm.
It tests for gross, immediate plastic yielding and physical leakage under a steady, one-time ideal load at ream temperature.
Yeah.
That is all it does.
Really?
Yes, it absolutely does not prove the vessel will survive the complex, dynamic failure mechanisms that actually destroy equipment in the real world. A hydro test does not prove the vessel can withstand the cyclic fatigue from millions of pressure swings or the vortex shedding vibrations we talked about. It doesn't prove it can resist creep at high operating temperatures.
Wait, creep? You mean the metal stretching?
Yes. At extremely high temperatures, steel slowly, microscopically stretches over years under constant pressure, like warm taffy. A room temperature hydro test tells you absolutely nothing about creep resistance. It doesn't prove resistance to high cycle corrosion fatigue from harsh chemicals or the severe thermal gradients and thermal shock of rapid startups and shutdowns.
It literally just proves the welders didn't leave a hole in it today.
Exactly. It is a baseline gross integrity check and a leak test. It is not a guarantee of lifespan.
That is a staggering realization. But speaking of thermal gradients and operating temperatures, this brings up another massive question from the field about what happens inside these vessels. The question is about refractory linings.
Refractories.
Yeah, these are the thick, heat-resistant, concrete-like linings sprayed or cast onto the inside of the steel shell in high-temperature vessels, like fluid catalytic crackers. The question people ask is, why do they always seem to crack? And does a crack mean the lining has failed and needs to be replaced?
They almost always crack. And it is usually not a failure at all. In fact, it is a necessary feature of the thermodynamics of the system.
How so?
Think about the physical state of that lining when the vessel is operating. The inside face of the refractory, the hot face, is exposed to intense heat, maybe 1500 degrees, so it wants to expand massively. But the cold face of the lining is firmly anchored to the relatively cool steel shell, which isn't expanding nearly as much.
Right, big temperature difference.
This massive temperature gradient puts the colder part of the refractory under severe tension. Concrete and refractory materials are incredibly strong in compression, but they are terrible in tension, so the material cracks to physically relieve that tensile stress.
So it's literally supposed to crack.
To a degree, yes. Furthermore, when the vessel finally shuts down and cools off, the hot face of the refractory experiences irreversible thermal shrinkage. This propagates fine shrinkage cracks through the lining. But here's the critical key to the whole system. When the vessel fires back up and heats up to operating temperature again, that massive thermal expansion on the hot face causes all those shrinkage cracks to close tightly together.
Oh, I see.
It puts the entire lining under massive compression. The load is perfectly redistributed, as long as the refractory was cured properly initially. and the heavy stainless steel anchors welded to the shell are holding it in place, that cracking is a necessary dynamic redistribution of thermal stress. It is not inherently a defect unless the process gas is getting behind the lining.
That completely flips my understanding. The crack is the solution, not the problem. Okay, back to testing the vessel itself. We covered the hydro test, but the text also brings up pneumatic testing, which uses compressed gas or nitrogen instead of water. And honestly, it paints a pretty terrifying picture of this procedure.
Pneumatic testing is incredibly inherently dangerous. It all comes down to the physics of the testing medium. Water is an incompressible fluid. If a vessel completely fails and rips open during a water hydro test, the pressure drops instantly to zero the moment the volume expands by a fraction of an inch.
So it's relatively safe if it fails.
Right. You might get a jet of water and the vessel tears, but the stored energy dissipates immediately. Gases, however, are highly compressible. They act like billions of tiny compressed springs, storing a massive amount of potential energy.
So if it fails with gas,
If a vessel structurally fails a pneumatic test, that rapidly expanding gas releases all its stored energy instantaneously. The vessel doesn't just leak or tear, it becomes a literal bomb. It violently explodes, destroying the shop and sending heavy steel shrapnel everywhere. You can mathematically calculate the stored energy of a pneumatic test in terms of pounds of TNT equivalent, and for large vessels, it is terrifying.
so why on earth would anyone ever authorize a pneumatic test if it's basically building a bomb in the middle of a fabrication shop?
Because sometimes the engineering constraints give you absolutely no other choice. Some process systems, like severe ultra-low temperature refrigeration loops or highly sensitive catalytic chemical processes, cannot tolerate even a microscopic parts per million drop of moisture left behind.
Because it would freeze or ruin the chemicals.
Exactly. And it is physically nearly impossible to perfectly 100% dry out the complex internals of a vessel after filling it with water. The remaining moisture would destroy the chemical catalyst or freeze and destroy the compressors. In other cases, the foundation design forces your hand. The vessel itself, or the structural steel holding it up, structurally cannot support the immense dead weight of being filled to the brim with water. A large gas column might be perfectly fine holding pressurized gas, but if you fill a 200-foot column with hundreds of tons of water, the concrete foundation would crack or the steel skirt would buckle under the static weight.
So if you absolutely critically have to do a pneumatic test, how do you not blow up the shop? What are the precautions?
The precautions have to be extreme. Because the test itself doesn't prove long-term safety and is inherently lethal, you have to definitively prove the vessel is nearly structurally flawless before you even apply the first pound of gas.
How do you prove that?
This means mandating 100% surface crack detection, using magnetic particle or dye penetrant on absolutely every single weld in the entire vessel, even if the base design code didn't originally call for that level of NDT. You use acoustic emission sensors during the test to listen for the microscopic sound of cracks tearing. You clear the entire area of all non-essential personnel. You put the vessel behind concrete blast walls or earthen berms if possible.
Wow, literally treating it like a bomb.
Yes. And you increase the pressure in very slow, deliberate increments, maybe 10% at a time, letting the strain physically stabilize before taking the next step up.
Okay, so if the physical test is either a limited snapshot or a potential bomb, what actually proves the long-term safety? That sounds like we have to rely almost entirely on the paperwork, the code, and strict, unwavering adherence to the rules. Let's talk about the pedigree.
In the world of pressure vessels, particularly under the ASME system, the pedigree is everything. It is the absolute ultimate proof of safety. It is represented by the physical ASME stamp hammered into the metal nameplate and the legally binding signature of the authorized inspector, or AI.
And who is the AI?
The AI is an independent third-party inspector who works for an insurance agency, not the manufacturer. Their sole job is to verify that absolutely every single minute requirement of the code has been met. Material traceability back to the steel mill, verifying welder qualifications, witnessing NDT results, double-checking design calculations, all of it. It is a rigid, unforgiving, highly bureaucratic system of total compliance.
But there's a murky, almost gray market underbelly to this, isn't there? The text mentions this concept of building to ASME intent. What exactly does that mean?
Building to ASME intent is a massive pain point in the regulatory, insurance, and purchasing world. It means a manufacturer used the ASME codebook as an engineering guideline. They used the formulas, they used the allowable stresses, they designed it well, but they explicitly skipped hiring the official authorized inspector.
Wait, really?
Yes, they didn't pay for the official third-party certification process. Therefore, the vessel does not get an official ASME stamp.
Why would a manufacturer do that? Is the inspector's hourly fee really that high?
It's partly to save money on the inspector, yes, but the motivation goes much deeper. Full ASME compliance requires incredible, burdensome administrative overhead. You need strict material traceability proving, with paperwork exactly which steel mill the plate came from, the exact chemical composition of that specific heat of steel. You have rigid, non-negotiable rules on exactly how much NDT must be done and who is legally qualified to do it.
So they just skipped the paperwork.
By building to intent, a manufacturer might bypass those strict material rules if they lose a piece of paper, or they might use a simplified NDT regime. They might X-ray the easy long seams, but skip the difficult nozzle welds to save time and money.
But the danger there is incredibly obvious. If you skip the independent checks, you don't really know what you have. You're completely taking the manufacturer's word for it.
Precisely. And the administrative pain point is that statutory authorities, like state boiler boards, insurance companies, and major corporate purchasers, will not legally recognize a vessel built to intent as a true, safe ASME vessel. It exists in a regulatory gray zone. It might be perfectly safe, or it might be fundamentally flawed because they cut a corner, but it completely lacks the verified pedigree. You can't insure it, and in many places you legally can't operate it.
If we connect this regulatory philosophy to the bigger global picture, how is this handled internationally? Because the text dives into the European approach, specifically the PED, the Pressure Equipment Directive, and it sounds completely different.
What's truly fascinating here is how the European approach differs fundamentally in its core regulatory philosophy. The ASME code is very prescriptive. It gives you exact rules. Do this, thickness must be this, weld it exactly like this. The PED, however, is performance-based and hazard-based.
So it looks at the risk.
Yes, it categorizes the equipment purely based on the inherent physical hazard it presents to the public and the environment. It calculates this hazard primarily by looking at the stored energy, which is essentially the maximum allowable operating pressure multiplied by the internal volume of the vessel.
So under the PED, a small low-pressure water tank is treated fundamentally differently than a massive high-pressure chemical reactor.
Exactly. The regulations scale with the danger. The PED charts also heavily factor in the physical state of the fluid. Going back to our pneumatic test discussion, a gas is inherently vastly more dangerous than a liquid because of that compressibility and explosive potential. So a vessel holding high-pressure compressed gas falls into a much higher, much stricter hazard category than a vessel of the exact same size holding high-pressure water.
That makes a lot of logical sense.
It does. The higher the calculated hazard category, the more rigorous the conformity assessment required by a notified body, which is the European equivalent of the authorized inspector. For low categories, the manufacturer can actually self-certify. For high categories, the notified body is involved in design review, material approval, and final testing. It's a completely tiered, risk-based approach rather than a strictly one-size-fits-all prescriptive one.
So wrapping this all up, it becomes incredibly viscerally clear that pressure equipment isn't just about plugging pristine numbers into a formula in a sterile, air-conditioned office. It's about anticipating the brutal, unforgiving realities of the physical world. It's anticipating the trucker hauling it over a massive pothole, the grain acting like a stone arch, the welder trying to force two warped plates together with a sledgehammer, the winter freeze turning your steel into glass, and the wind trying to shake it to pieces for 30 straight years.
It really is the ultimate collision of theoretical physics and heavy industrial reality. Every single rule in that code book is written in the wreckage of a failure. And I want to leave you with one final thought to mull over, especially as our industry rapidly evolves. We are currently moving aggressively toward an era of AI-driven, computationally optimized design.
Oh, absolutely.
Finite element analysis algorithms can now effortlessly shave millimeters of thickness off a vessel shell to perfectly match the theoretical stress, saving massive amounts on material costs. They can create a mathematically perfect, hyper-efficient design with zero wasted steel.
Which sounds great for the budget.
But this raises a vital, terrifying question. By optimizing away every single ounce of excess steel, are we actually engineering away the very forgiveness, that brute force safety margin, the uncalculated excess thickness that currently saves our vessels from the unpredictable quirks of manufacturing misalignments, transit damage, and operational abuse? Will computationally perfect math actually lead to far more catastrophic failures in the messy real world?
Waste is inevitable. Excuses are optional. Build better next time.